We'll be starting in a few minutes, so let your batchmates and juniors know and ask them to join soon.
Okay, let me try
Hello, sir.
sharing the.
Yes, we are doing great here. I think it's really early for you over there, right?
It's 8:30, not that early, but yeah. Um, Let me actually try sharing my slides so
Yeah.
that we can make
Thank you
sure
very much
everything
for.
is set up. Yeah.
Yeah, yeah, yeah. Yep.
Can you see it?
Oh, yes. Yes, clearly visible. Yeah.
So when do you want to start? 8:30 or a little bit later?
Yes, sir. We can start in 5 minutes, I can. Yeah. So we can start.
Okay.
Yeah.
Yeah. So hi everyone. I am Amanpreet and I currently working at Hugging Face. And before this, I was working at Meta AI Research. And today I'm going to talk about the topic towards unified foundation models for. If you want to follow my work more, like you can follow me on Twitter, where I mostly post anything related to my work. Uh, so let's talk about the agenda today. So this is almost going to be a 45 minutes talk. So there is a lot to cover. So we can start with the recap of like some things that are relevant to like understanding the work that I have done. And then we will learn how to build a unified foundation model. I will go into more details of what I mean by unified foundation model. And then how do you pre-train it? And how do you like step up the evaluation in the sense to meet the criteria of the today's models because they are getting more and more advanced, so the evaluation is still behind. So how do you step up the evaluation to make sure that you are targeting the right capabilities to test? So let's start from a basic recap of transformers and intentions. A lot of you might already know this, but just for the sake of like people who don't know about it, I can start from like the intuition behind the attention, like why exactly and it works and what is the main idea behind it. So this picture I like it a lot because it shows you like what exactly we mean by attention when we do sort of like some sort of like softmax over some things. So in this example, like the first one you see, so when you like are conditioning something on frisbee, then it should like in the image focus on the part of the frisbee in the image. So by attention we mean like depending on the input, like where do you focus in the conditioned input. So it might be a little bit confusing, but you just see like the upper sequence. This shows like at for a particular caption, where does a model focus for each of the words. For a bird, it focuses on the complete word, and then for the flying is some of them are like very abstract in sense, like the flying is abstract. So where do you focus? Not really clear. But like if you see water, body, bird, over, like example, a good example is in this one is the third example where like a stop sign on the road with the mountain in the background, and for the stop sign it specifically focuses on the stop sign itself and nowhere else. So we are trying to like apply attention on the image conditioned on the input text that is given with us. So for every word you attend on different parts of the image so that you can get a correct um, output embedding for that particular image. So this is basic concept of attention, like, but how do you implement in like a mathematical way? We can talk about it in a little bit detail. So this is a good example. Like first time when attention was shown, like even in the Transformers paper, it started from machine translation. But this is a good example because you can see, like in this case, like this is self-attention, where the sequence is attending on itself. So when there is a word like it, which is ambiguous, like what does it points to? You want to get a representation of the it, which is more relevant to what it should point towards. So for the it word in this same sentence, it points to the animal as like the most heaviest weight. So like see the description below, as we are encoding the word it in the encoder, the part of the attention mechanism are focusing on the animal, and it's baked into the representation of it. Like it means the animal. So that's why attention is important in like understanding the correct representations of the words or like anything in a particular sequence. So you basically apply it as a probability distribution on the sequence that you care about. So the words, or like let's say the elements of the sequence which you care more about, you will apply higher probability on them, and the ones that you don't care about, you apply lower probability on them. So think of it like as a weighted sum. So you can like apply a probability distribution which upsamples the things that you care about and downsamples the things that you don't care about for the particular conditioning that you are doing. So like I said, like this distribution is calculated based on some condition. And then weighted sum is used in further layers. So you can like apply that as long as you can represent an input as a sequence, you can apply attention on top of it. You can apply it in other ways also, but it's generally more intuitive when you're applying it on like sequences. So let's talk about transformers in a little bit detail, but first we'll go into like a proper mathematical formulation of attention. So we were talking about the conditioning, right? Like where do you condition, how do you condition something on like a, how do you condition an input on a something that is a separate input? So in this case, we call it a query. So for the query is the condition that you want to condition the input on. So, and the key and the values are the input in most cases. They can be separate, but in most cases, key and the values are the inputs. So attention where you basically multiply query, you do a dot product of query with the key. Then you like understand how much each of the elements among the key matter more, or like how much query affects those keys. And then you take a softmax and then multiply it with the input itself to get input itself. So this is how attention is formulated. And we basically like put attention inside like an architecture called transformers, and this is how transformer formulates the attention. So see this under root dk, this is the dimension of like the key and value. So this basically you have to divide it, otherwise in general practice when you train it, the equation becomes a little bit unstable. So you basically divide it by d under root dk, and you generally see better results by doing that. So you also like in some cases, like if it's like causal, right, like in the sense you can't see what is happening later in the sequence. For example, when you're generating text, right, you generate a word for further connections that are auto-regressive in nature. So you need it in some cases, such as language modeling. So you basically can do it, you can scale this dot product attention by like having multiple heads which are doing learning a different sort of attention mechanism. So this is what we call multi-head attention. So like this applied in multiple layers, like this attention mechanism applied in multiple layers gives you a rector, and this particular block that we are seeing on the right side is called a transformer block. So you take an input embedding, you apply self-attention. Actually, let me see, why isn't this working? Trying to get my laser pointer on. Yeah, so this thing, can you see my laser pointer, any of you?
Yes, sir.
Yeah, okay. You pass it inside this transformer block as a sequence of patches, and then you just tell it like in the position embeddings, like where exactly each of the patch is. It did work really well out of the box. This was a very surprising result in the sense, and this was the start of transformers taking over like the vision community as well. So there are like pre-training mechanism in here also. I will talk about them a little bit later, but basically you can do the same thing that you're doing here in the masking. You can mask these patches and try. Each of these words belong to a vocabulary. Thus, you can try to predict what is the index of this word in the particular vocabulary. So it's a classification task. But here is no, there is no such luxury that you can put this particular patches into a vocab. So you try to regress over the complete mask. This particular talk, like how do you combine these transformers in both sides, like on the vision and the text, with the problems that actually care about both of them. So think about image captioning, where like there is this image and then there is a caption. So you can try similar sort of technique as BERT, but you mask the caption and you try to mask the caption. You try to unmask the caption based on the image itself. A good thing is like if you mask the whole tennis racket, right? You can't like probably predict with high confidence like what exactly here was. Like it can be like a bat, it can be like a baseball bat, it can be something else also. So you basically need the image to like figure out what exactly was here. So this problem is a little bit interesting in the sense that this does lead to like really good vision and language transformers, which can attend over both of them and then do some sort of reasoning over top. So one of the pioneer models in this one was Visual Bird. This was actually released almost like 7 to 8 months after the bird. There were a bunch of them that came together, like Billbird, Visual Bird, Alex Nerd. There's so many of them, but this is the one that's most simple and was very effective in their nature. So let's talk about what we are going to actually talk about today. So we are going to understand like how do we build foundation models that can solve tasks across modality. So something like Visual Bird, but efficient and proficient in everything. So the question is like, why do you want to do this? So by here, I mean by modalities like image and text, but it should be able to solve image and text separately as well. So in Visual Bird, you can't solve just images. Like so by solve, I mean like do any sort of downstream task on them. And you can't do anything on top of text also alone in Visual Bird. You need the combination of two. But how do you do it across modalities that can handle both vision, text, and vision and text combo as well? But then the question arises like, why do you want to actually do this? Why does this matter? So as of now, like before, like now it has changed a lot, like since FLAVA came out originally. Like even for BERT, when you fine tune it for each of the tasks separately, you end up with 10 BERTs for 10 tasks. So this is not something that we actually want in practice, because if you are like trying to solve n tasks, you will need n models, and this is not resource friendly because inference compute will be more required, and you will incur more and more cost in them in those particular areas. So for example, like before when faster RCNN was very famous, like it would have two heads, like object classification and the bounding box regression heads, and you would want to like share these. So how do we get like this whole trunk was shared in this particular architecture? How do you get this in like a multi-model scenario, right? And even here, like these are very star specific architectures, like specifically for open-ended QA, where there is a retrieval, ranker, and then you pass it to like some model, and then it basically gives you answer. These are so cumbersome in that sense. Like the community wants to move away from all of this. Then there is like other things like there's no sharing of knowledge and resources in most of the cases. Like for example, like at least in BERT, the trunk is shared, right? You can use this common knowledge to like fine tune on different specific tasks. And there is another problem, like the shared task trunk and the multitask was working only in a specific domain, either in NLP or either in vision. So there's so many like things of why you want to do this, because we want to achieve an architecture or a trunk that can work across modalities, and then you don't have to like fine tune across modalities. There's another side effect that happens in practice is that once you start learning from images, the text actually gets better. And then when you learn text from text with images, the images also get better, because if you see just the image of elephant, you won't know in practice like how big elephant is compared to something else if you're only seeing only the images of the elephant. So text can help compensate that in some sense. um, so the key challenges is like why this is hard. So the first thing is like jointly learning across domains is hard because they're actually very different in generic nature of how they actually are presented and the amount of data that they require. So for example, like before when faster RCNN was famous, like it would have two heads, like object classification and the bounding box regression heads. And even here, like these are very star specific architectures, like specifically for open-ended QA, where there is a retrieval, ranker, and then you pass it to like some model, and then it basically gives you answer.
Amanpreet has disconnected. Please hold on for a few minutes. Uh, Uh,
Sir, you're mute, sir.
Yeah, when did I drop? About what time?
like 30 seconds ago.
Okay. Yeah, then I noticed like this wasn't there. So where was I in this particular slide?
Sir, you have not shared your screen, I think.
Okay, give me a second. Sorry. Can you see it now?
Yes, sir.
Okay, so is this a good starting point to start again?
Yeah, sure.
Okay. Uh, so I was talking about like the shared trunk. Like if you don't basically have like a shared trunk between different modalities, you will have to like pre-train it again and again. So basically, you want to solve all those tasks together. So a good example of this is like think about Facebook, where like most of the posts are like multimodal, like in the sense like there is an image and some text that people put with it. So you would want a single model to understand both of the modalities together. So this is why this is super important. So the key challenge here is that the jointly learning across domains is like super hard. So when you try to do multitasking, the model either goes into like a vision direction or either like a text direction, like it tries to like move into like a certain direction. So you have to like control this. So make sure that this doesn't happen. So this is why the multitasking aspect becomes a little bit harder. And then also like catastrophic forgetting happens for unimodal domains when multimodal domains are introduced. What I mean by this is like if the model was working fine before for like text separately and image separately, as soon as you start introducing the multimodal domain where there is images and text, the catastrophic forgetting starts happening. That it starts forgetting about any sort of the unimodal domains. Like it just like becomes specialized for multimodal where it sees both of them. Again, like the architect. So this is one of our photo from one of the papers where we want to solve object detection, visual question answering, and the glue task from a single model. Like this is everything. So given like what is the color of the woman's jacket, you will need the image for that. And then for detection, you just need the image. And for the other things, you just need text itself. So, but can we handle multiple architecture that we build in the unit paper, which is unified transformer? So it's simple, like we have seen the transformers before, like the transformer architecture that I explained. So this is like only the self-attention part. So you take an image, you apply a ConvNet backbone. So this was before VIT came out, so a little bit before that. So we were only using better style architecture where you basically have a ConvNet backbone and then you have a attention transformer on top. So you take these outputs from the ConvNet and then you pass them through an image encoder. And here you get like a contextualized representation of the images, which are like self-attended. Same for the text side of the things. You get like a text input, a text contextualized outputs. Think of it like a BERT, which gives you like a CLS representation out them. And then you basically have like a multimodal decoder, which based on the task query, like some task query, like which tells you which sort of task you are trying to do, it will decode these two into like a correct output itself. So based on this, you can have like task specific output heads. If you're like solving detection, you will have like a regression sort of like regression head. If you're solving weaker, you will have classification head and so on. So based on this particular query, this tells you like, okay, among this particular concatenated output of image and text encoder, what matters when I'm like doing detection. So this is the job of the query to tell the model like what I need to like concentrate on depending on the task at the head. So the image encoder we already explained, and the text encoder is very similar to BERT. So you can like do this together using this query embedding, and in practice it works super well. So you can basically just take like different inputs, get outputs from query embeddings, and then you apply a task specific head, and it does work. But in practice, it's super hard to train. Like you require very careful control over like how much you sample from each domain. So that's the hardest part in making it train. But if you have like a right schema of how you want to sample it, it will work. So these are some of the examples from this particular model. But the question is like, can you take it step further? Like this is supervised pre-training, right? Like you are basically taking all our tasks and then passing it into the same model and then generating something on top. But can you take a step further? Like, can you make it even better? But why do you want to do it? Because you don't leave a model without pre-training. So you have to do pre-training in current era because you're just losing on a lot of data that is unstructured and available in the world. So how do you take it one step further? Saw a lot of examples, right, in the initial slides, like BERT, and this was the masking architecture that I was talking about. You mask the patches, and then you pass it into encoder, and then you have like a decoder at the end, and then you basically try to like generate the masked patches, like regress to them. This is the clip architecture, which has been like quite prominent in like multimodal field, where you take a text and image encoder and then you try to do some sort of contrastive loss on top to make sure like the text understands which image it matches and which images it doesn't match. So you give like positive loss on these, like on the diagonals, and like some sort of negative loss on like the off diagonal things. So this, what it happens is the embeddings that you get from the text encoder and the image encoder, they align for like similar sort of image text pairs which match, and they like move further away from each other for the text and image pairs that don't match. So this has a lot of like downstream implications because now your image encoder is grounded in text and the text encoder is grounded in the image. So you have like an image encoder that is better for like any sort of text task that you want to try to do. So this is the Wilbert paper. And so we had like a lot of things that were happening at that point, like pre-training, train once, but use many times, right? So what are the key challenges if we actually want to do this even further? Like, so the one of the problem is that the crossed modal like image text caption pairs are not abundantly available. So this was at some point like Lion wasn't out there, like the Lion dataset, which is like right now the biggest dataset, but not clean. Like in these first, they were like more data sets used, which were never open source. They were internal Google. So they were like never released. So there was no way that the field could make progress on this. So how did we circumvent this? So we collected we basically like went over the web and collected all of the image text pairs that were present publicly. And we got almost like 70 million of them. And these are the sources from where we got them. So there are a bunch of them. So in the end, we had a 70 million data set, image text data set, which was the biggest at that point. What is the next problem? Each other, like if you're trying to do text MLM, it doesn't really align with like the MIM on the other side, which is masked image modeling. And the contrastive law issues with masked image modeling because contrastive loss cares about like aligning the image into the text, but like MIM just cares about the image representation. So these also require massive compute because if you train it on like smaller batch sizes, it doesn't really yield anything. It's like these models are big, you need like a lot of compute to do anything with them. And many vision language like models are also not open source. So let's enter FLAVA. Like this is one foundation model that we built across CV, computer vision, NLP, and vision and language. This was single model that had like impressive performance on 35 tasks across 3 domains. Like it could do vision, it could do NLP, it could also do like the combination of the two. So this model was the single model at that point that could solve these many tasks. And then all of the data and the models are public for this one. So okay, let's talk about the problem, like how exactly it works. So think about this. These are the 3 data set scenarios that you have actually occurring in the world, just for image and text. You have image text pairs, like the ones that we talked about, 70 million ones. You have unpaired images that don't really have any text associated with them. This is what most of the images in the world are. In our specific case, this is ImageNet. And then there is unpaired text. All of the web is basically unpaired text. You can use all of it. And what you want is something in between that can capture this. And then it can do visual recognition, language understanding, also the multimodal reasoning, similar to like Unit, but you are trying to pre-train it. So basically we do like multi-domain joint pre-training. We have a contrastive loss, triple M loss, MIM loss, like which is triple M is masked multimodal modeling, where you like mask on both sides and try to predict each other. MIM is masked image modeling, just mask the image. MLM we talked about is the BERT loss. So how does it look like in practice? So now, like because VIT was already into the picture, the convolution block is gone here. So you take the image, you split it across the patches, you pass it to the image encoder. For the vision task, instead of like relying on the multimodal somewhere here, multimodal encoder somewhere here, you will just apply it on top of the image encoder itself. Even the task specific pre-training loss, you will just apply it on the image encoder, because the multimodal encoder doesn't need to know about the image specific task. Same on the text side, you will do this same thing. You will have a text encoder. You will apply an LP task on top of this text encoder, and same the pre-training task. And then you pass it through this encoder, complete encoder, and then you apply the multimodal task. So this is the global contrastive loss that we talked about, the lip. Sorry about this. I'm not sure like why it's like keep on killing my tab.
Right, it's absolutely okay.
Yeah, so it just kills my tab, and maybe I'm running out of memory. I'm not sure, but the whole rest of the slides.
Yes,
Uh,
hopefully. Yeah, please share your screen. Okay.
yeah, I'm doing that. Give me a second. Yeah, so I was talking about the losses. Let me actually check. Give me a second. It shouldn't do it. Yeah, sorry about that. Okay, so I was saying like there are like bunch of losses here that basically like combine with each other, but they are all like sort of sometimes fighting with each other, but they're also like complementary. So the interesting part here is that we don't apply any weighting on any sort of weighing on any of these losses, but it does work out of the box. But what you have to make sure is when you are like passing images inside the image encoder or text encoder, you sample them accordingly. You don't want to like sample too many images alone, or too many text alone, or too many multimodal like pairs alone. So this is a little bit hard because you have to like get to this schedule of like how do you actually want to sample it, which matters a lot. So in practice, like it works actually much better than unit and clip for like that text task, because clip wasn't really good at text tasks, like, but our model is super good at text tasks. Like, and but it has like a lower image net accuracy, but not as much low. But if you like start fine tuning it, it will become much better. But the major difference you see is in the multimodal task, where like you see much higher numbers than clip or any prior model in that sense, even visual which is specifically trained for multimodal tasks. So this tells you like if you also learn a language only task and vision only task with multimodal task, it will lead to like a better model than just using them alone. So the field came out, but like this was like one of the initial works where like we showed like, okay, if you leverage all of them together, then it will lead to better performance overall. So yeah, so the final challenge that I wanted to talk about was like the current evaluation benchmarks are not relevant and are saturated. So this is the graph from our adversarial VQA paper from Neurips 2021. So what exactly happened here is like as the field is moving forward, there's so many changes happening with transformers, pre-training, and everything. Like the human accuracy is almost like 82%, almost close to that. It's a little bit higher than that, but like the models are getting super close to this particular human accuracy, but work. So we want to like actually create tasks which show meaningful capabilities and not just saturate like VQA. So hateful memes is one of them that we created. So if you see like the text on both the memes in this side is same, but one is actually hateful because it shows a skunk here. So you have to like disentangle the multimodal signals from the unimodal signals to make sure that you are understanding whether the meme is hateful or not. So same in the lower one, like the left one is hateful and the right one is like not hateful. So the best model on this one was 78.4, but FLAVA as a unified architecture performed really well. And Winound is like one of the hardest tasks for like multimodal settings. Like if you're interested in doing research on multimodal, this is one of the tasks to look at. So what happens is like you have like a two set of images and two set of text, but in the text, you have the same text, but with the word order change. It basically changes the meaning of the sentence itself. Um, so if you see the right one, a light bulb surrounding some plants, and the left one, some plants surrounding a left one, they are both different in meaning, but we want our model to match it properly. Like it should know that this image doesn't relate to this text and this image doesn't relate to this text, and vice versa. This image doesn't relate to this image and this text doesn't relate to this image. You get a full score when you can like do the all set of four comparisons properly. So best is like really, really low, like it's almost like close to random, like 14.5. FLAVA also doesn't do a good job at it, but this task in general is super hard because these models get confused because they learn through attention, right? They never, in most cases, they never learned like what does the word order means in that sense. So that's why we want to test this, that actually the meaning of the sentence has changed, but the model is still paths of the data coming through. Paths of the data coming through.
All right then. That's good. And maybe I was recently I was going through this instructor embeddings. So do you know about that? I think
Yes,
the hug.
so there are a lot of embeddings in picture, like like there are rotary embeddings, there are instructor embeddings,
So,
bunch of them, but they all have different sort of improvements.
yeah. So for you, what could be a good embedding? Sorry, transformer module that gives us embeddings according to a task specified for maybe say text.
Yeah, so for right now, you can basically use BERT, like to start with, like BERT style architecture, then you can move forward because there's a difference between encoder, decoder, and encoder models, right? So there's also decoder models, which are just decoder models, but we wanted representations out of the model, so we used encoder model. For encoder decoder, you have T5, so you can probably leverage that. But if you want to use decoder models, then you have to look at the new series of work, which is like Blip 2 and others, where like basically, so this is getting more technical in that sense. So maybe like most of the audience won't understand, but what happens is that vision encoder, you get out an embedding, then you try to project this embedding into model. Let's say Chat GPT, you don't have weights, but for like GPT-2 and like any other like OPT or Lambda, you can basically Llama and like Lambda and others, you can project the vision embedding into the space of that language model. And then you basically use this as a prefix to the language model. So that's something that you can use. But to start with, I would always start with BERT, nothing more than that for text side. And for the image side, you can now use VITs, vision transformers, so they are really good. In our case, for FLAVA specifically, we trained from scratch, like without anything. So we didn't have like those problems. Like we were sharing the, so on the both side on the image and the text, we had the same architecture, and we pre-trained them from scratch itself.
Right, yeah, yeah. So in your slide, so I saw that it had three modalities. So it could have image and text together, or image or just text.
The image and text come through separate towers, and then you merge them into multimodal encoder. So you can extend this architecture to like audio or video also, where you can add like a video specific encoder or like audio specific encoder, and then you can merge them together.
All right. Yeah. So that's the adversarial part of the training.
Yeah, that's
When
where the
you're
problem happens. Yeah, when you start merging, like it starts moving towards the multimodal scenario because it just there's a catastrophic forgetting that happens because it has to like specialize in different mechanisms, right? So out of the box, it doesn't happen like that. So you have to like make sure it doesn't forget the previous things that it learned for the unimodal domains. So you keep on like pre-training on unimodal domains as well. Any other questions? Hmm. If not, going once, going
Yeah,
twice.
I had
Yeah, go
one.
ahead. Yeah.
So I think the approach that we took to basically of basically applying the cross attention that is happening only between again, of course, it happens between encoders and decoders. But do you think uh, way that we are approaching cross attention, that do you think we need a different way of attention mechanism if we want to deal with multiple modalities at the same time?
Are you talking about unit or flavor?
Unit.
Yeah, for unit, yeah, we are like handling like um old unit anymore. Flavor is like a superset of it in any sense. Like you can just use flavor anywhere you're thinking to use unit, except like detection. Like flavor doesn't work on detection because it doesn't have a regression. But in practice, you can fine tune it on regression as well. So flavor, there is no cross attention happening. Once you like combine the image and text modalities outputs, you are basically doing a self attention on the complete sequence. So there might be ways like a lot of thing in a lot of papers, like what happens. That's also like one way of like doing this. Never like directly merge the embeddings. You basically always have two towers and then you like do cross attention between them. So that's one way of doing it. The like if you are interested in it, you should check the Wilbert paper, which was the original paper that did this in cross attention mechanism. And the newer ones, like the brothers, are also doing something similar with text and the image when they're conditioning the text on the image itself. So yeah, there can be like different ways of doing it. Like some may be better, some may be like more efficient. But in practice, like it doesn't really matter as long as you can throw like a lot of model data on the model and you have enough compute. Like in the end, like the scaling laws, they basically set everything same. Like the model will learn how to like do it. You need to have enough data and
Okay.
good losses in that sense.
Just to conclude our answer, from all the studies that have happened till now, which try to use different attention mechanisms, or maybe or not using attention, some using some other mechanisms also, it turns out that all of them converge to to almost the same point if the amount of data thrown and losses are
Yeah.
good.
There is a paper on this, like which studies different attention mechanism and vision transformers that have happened in the last two. I need to find it, but the paper basically says like none of these matter as long as you throw enough compute and data on the model. Like even the newer, the original attention mechanism is enough. That's what that paper concludes.
Got it. I also had a question unrelated to this. A generative task or a discriminative task, either way, uh, handling becomes very cumbersome during the training process, because it's like often the two losses start decreasing together, but at some point it turns out they are kind of rivaling out in themselves. So do you
Yeah.
have any tips or tricks for that on how to overcome it?
Yeah, I think you need to understand the relation between the losses for this specific case. Like most of them were like complementary to each other, so it didn't cause a lot of problem. But if you have like adversarial losses which are trying to like move the model into different direction in that particular area, you need to like think about whether you are using the right loss or not. Maybe you need to do something else. Like make sure they are not like different directions. So what you want to do is like pre-train the model with first loss first and then the second loss afterwards. Do some sort of PCA analysis to see where the embeddings end up in general. Like if they're ending up in a very different domain, then the losses are not in the same sort of like uh, they are not complementing each other. They will be always be pushing the embeddings into different direction. So you have to do some sort of qualitative analysis of the embeddings to figure out how far they are pushing to each other. If that happens, then you can't really fit both of them together. You have to like make a choice which one you want to sample more. So more you sample the one of them, the other one you will be not pushing as much, but might be like giving something. But if the laws are anyway like not complementary to each other, there's no point in adding the other laws, because it will just decrease the performance of the model. So it's like a game of trial and error where you figure out whether this loss is complementary or not, and doing some sort of qualitative PCA or like other sort of like analysis of the embeddings would be very helpful to you.
Okay, thanks. One last question. Any way on, like, if it is not already, if I cannot already get it through intuition, any heuristic way to find out, okay, whether these two losses are competing with each other or not? or is it just by looking at the loss curve and that's all we can do?
You can also like see downstream evaluations, right? Usually loss curve is not the final thing that you care about. You usually care about some downstream metrics. So you should check if the metrics are going down over the curve of the training. You should have like a validation set, and as you train, you should evaluate it at a certain intervals and then check what is the graph or like the plot of the metrics and how they're dropping over the time. So if they are like dropping weirdly or like not doing as good of the job or like are not increasing, then you will
Yeah,
figure out
got it.
whether what
Got
is
it. Thank you
happening.
very much.
Yeah. Yeah. Anyone else? Any questions?
Yeah, so hello Amanpreet, Krishna here. So like I would
I
like to comment on the when you said during the pre-processing you are just like embedding with the positional encodings, right? In the flavor part also.
Yes.
So like you said that
Yeah.
they doesn't process the linguistic structure of the whole language. So rather than taking the positional encodings, what about we take the relative position embeddings instead?
I mean, technically, it should work with positional embeddings also because it does know like this was at the first place and this was at the second place, right? But there are papers you should search on this. Word order doesn't matter. There's a specific paper from Ethan Perez, like that shows you that these models just start ignoring word order in um, when they're like trained in this way. Yeah, you might want to use try relative position encodings, but I don't think in practice that helps because FLAVA is not the only model that we evaluated on Phenoground. We evaluated a bunch of others, and none of them were working at that tactic and semantic structure to like actually solve this task. And it has been like what 1.5 years since almost like 1 year since Phenoground came out, and we haven't seen any progress on the task itself because it's just too hard of a task.
Okay, yeah, so like basically rather than focusing on natural language processing, we should focus on the natural language understanding aspect of the like,
Yes.
yeah.
Yeah. Yeah, read this paper. Word order does not matter. Like I think that will give you more idea on like why this is happening and why what can particular problem.
Yeah, so like actually there was paper after the attention itself, Vaswani, that they introduced the relative positional embedding. So like I
Hmm.
thought that might
Maybe
work it out. Yeah.
maybe you can try. Like it's not super hard to, but you will have to pre-train the model, which is tricky. So
Yeah, I don't have the resources. Yeah.
yeah.
Okay, thank
Um,
you.
okay. Any other questions?